Hi everyone, my name is Will Harcourt and I'm a third year PhD student in the School of Physics and Astronomy at the University of St Andrews. The goal of my research is to develop the capabilities of unique radar sensors to map and monitor the dynamics of glaciers, those icy and fragile environments that have become the symbol of climate change as we know it. So let's firstly consider what a glacier is. Snow falls at high elevation. If the snow survives a whole seasonal cycle, multiple layers of snow will form. Over time, the layers of snow press down on the layers below, squeezing the air out of the volume and eventually creating ice. Once formed, the ice will continue to grow through this same process, and as the ice grows, its own weight will force it to move downslope towards the sea. The ice will continue to move towards the sea, but will be restricted by the warmer temperatures at low elevation, causing the ice to melt. If this melt is strong enough, the glacier will terminate on land, where it is called a land terminating glacier. If the melt is not strong enough, the ice will continue to flow into the sea, where it is called a marine terminating glacier. When a glacier terminates in the sea, icebergs can detach from the end of the glacier in a process known as calving. The combined process of melting and calving is known as ablation, and the addition of snow is called accumulation. The difference between these two quantities is defined as the glacier mass balance. If the mass balance of a glacier is negative, it means more ice is being removed and the glacier is unstable, which is the case for most glaciers on the planet because of the warming climate. I want to focus now on this process, iceberg calving, which is the process driving sea level rise in the present day. The process of iceberg calving occurs when a crack penetrates through the entire glacier and an iceberg breaks away into the sea. This video shows an image sequence from a time-lapse camera in Greenland, which captured this large 75-minute calving event, which has been sped up into this 22-second video. You can see lots of processes going on here. There are icebergs of varying shapes and sizes breaking off the glacier, and these bergs are capsizing and creating large tsunami waves, which impacts the stability of the glacier. So, lots of processes going on in a really short space of time. Let's now take a look at a similar event, but this time with satellite imagery. This time-lapse is also of a glacier in Greenland, but this time created from satellite imagery in August and September 2019. You can see the ice advancing as it flows into the sea, but there are periods of sudden retreat, which indicates ice has been removed from the front of the glacier through calving. So in these satellite images, we really can't resolve the fine-scale detail of these calving events, especially when we compare it to the ground-based time-lapse video we saw previously. And a more general point from both of these time-lapse videos, cloud cover becomes a really big problem, and we can't image the glacier properly when it's covered by even just a small portion of cloud. This is a big problem and requires a solution. To solve this issue, we must consider what it is we are actually measuring, the electromagnetic wave, which is found on a continuum of waves of many lengths known as its wavelength. As humans, our eyes are sensitive to visible light, which is the same light cameras use to take pictures, and are very small waves at the nanometer scale. On the other side, we have microwaves, long waves that can be up to a meter in length, and it is these waves which radars use for their measurements. The wavelength that you choose for a particular instrument dictates the type of measurement you can take. For example, radar sensors have a lower resolution compared to optical instruments such as cameras. And as I alluded to before, Instruments using visible light struggle to see through clouds, yet radar sensors can do this. So, as scientists, there is a big decision to make here. Do you favour resolution and measurement detail, or do you favour being able to take measurements in all weather conditions? Well, my research argues that we don't need to make this decision, and instead we find a middle ground and take the advantages of both optical and microwave instruments. This middle ground is the millimeter wave region of the electromagnetic spectrum. Millimeter wave radars can obtain high-resolution measurements in almost any weather condition, thus taking the benefits of both microwave and optical techniques into a single sensor. This is the basis of my current research, where I am developing the use of ground-based millimeter wave radar to map and monitor glaciers. These are hostile environments with equally harsh weather conditions, making them ideally suited to being monitored with millimeter wave radar. To test how well millimeter wave radar performs in mapping glaciers, last summer we deployed our system at Glacier in the Swiss Alps, which is shown in this map here. And here is a time-lapse video showing the millimeter wave radar in action. And I have to say, field trips to amazing places like this will always be the highlight of my research. And the weather couldn't have been better for it either. In terms of what's going on in this video, the radar is scanning across the glacier, transmitting a signal and measuring the strength of that signal after being scattered from the glacier surface. We can measure the distance to the glacier by measuring the time it takes for the signal to travel to the glacier and then back again. And we can do this because the speed at which the signal travels is simply the speed of light, which we know is 3 × 10⁸ meters per second. What I am showing here is the first millimeter wave image of a glacier ever recorded, which is pretty exciting. The image is a bird's eye view of the front of the glacier, and the dotted box in the image above outlines the area that we've mapped. The labels A, B, C, and D all correspond to locations on the glacier. As you can see, the radar can pick out key features such as the icebergs, the main ice body, and the valley side, all showing varying degrees of brightness. The tarpaulin cover, which is labeled D, hides an ice cave below it, which is used as a tourist attraction, and this cover is there to stop the ice from melting each summer so that the attraction is preserved. This image in itself demonstrates the ability of millimeter wave radar to map out the features of a glacier surface at high resolution. And as a final illustration of how well millimeter wave radar performs, we have used the data from the previous slide to generate a 3D model of the glacier surface. This model elegantly displays the rugged shape of the glacier surface, whilst it can also be used to distinguish different terrain types, such as the valley sides, the main ice body, and the tarpaulin cover. Just like before, this is the first time we've been able to generate this kind of model using millimeter wave radar. So these are just examples of the kinds of data we can produce with this type of radar. If we want to monitor processes such as iceberg carving, we must generate these datasets multiple times over a defined period of time, and this will be key to the next phase of this project. In this video, I hope that I've given you a flavour of my research and the many strands it has taken over the last few years. The challenge of climate change is a global one, and developments in technology will continue to transform our understanding of the world around us. And on that note, a big thank you for listening, and please get in touch if you want to know more.